Hello, Ayomide. Can you hear me?
Sir?
Yeah, good morning.
Yes, sir.
Yeah,
Good morning, sir.
I'm checking my mic. Oyin, can you hear me? And can you see what I'm sharing on the screen?
Yes. Yes, sir.
Oyin, Precious.
Yes, sir, I can hear you, sir.
Okay, can you see me too?
Yes, sir.
Okay. What about Anoluwapo? Anoluwapo.
Sir?
Okay. Gabriel Tolu. Gabriel Tolu. Okay. Who is Adewumi? Ifeoluwagbola. Can you hear me? Oluwaseun. Can you hear me? Okay. So you can actually mute yourself when you want to talk. So we'll start the meeting in the next 2 minutes. We have just 14 participants. So I've asked you all to write your names. You can just put your name and matric number in the chats section. So we're expecting a lot more. Where is the class rep? Tolu, are you there? Tolu, who is the class rep? Is the class rep there? So a bit slow. All right. So we're going to be looking at the topics I've highlighted here. Water and chemical properties, definitions of acids and bases, pH scale and measurements. I hope you can hear me well.
Yes, sir.
Not too loud.
Yes, sir.
Okay. So pH scale instruments for pH measurements, derivation of Henderson-Hasselbalch equation, the relationship between pH, hydrogen ion concentration, hydroxide ion, KW, and pKa. I'm going to go beyond that, I think. Let's just move on. So we know now this structure of water, that's the hydral structure of water. You can all see that the hydrogen atoms confer on water a partial positive charge, and the oxygen confers on it a partial negative charge. So when you talk about the dipole, a dipole, just like we're talking about monoprotic, diprotic, the dipole has what? 2 poles. Now, okay, so the dipole has 2 poles, and as it is here, a positive pole and a negative pole. Now, structure allows water molecules to form hydrogen bonds, and hydrogen bonds are basically non-covalent in nature. They are weak but important, because you have a lot of water molecules forming at least the water molecules with, as you can see on the screen here, the water molecule forms hydrogen bond, and this central water molecule forms hydrogen with about 4 others. So, and you can see the points of hydrogen to oxygen, another hydrogen to an oxygen, and then the central oxygen of that molecule forms hydrogen to other water molecules via their hydrogen atoms. So basically, the ability of water to form hydrogen bond is quite important to its function. Now, you know very well that water is present in living organisms. It is one of the predominant chemical components that you find in living organisms, and it forms a larger percentage of what you find in the kind of biomolecules you find in living. But it is also central to a lot of. Can you hear me? Are you there?
Yes, sir.
Yes, sir.
Okay. So we all agree that hydrogen bonds in water is quite important to the properties of. I'm having a class. Now, without referring to whatever you did yesterday, they have a slight but important tendency to see it. It's something that we need to describe. I want to use it while talking about acid-base chemistry. So I like to refer to water molecules. Now, water molecules, according to Bronsted definition of acid, water molecules are acidic because they can donate protons. They are also basic because they can accept protons. So if 2 water molecules react, one would be behaving like an acid, while the other would be behaving like a base. Now, if they react, you expect that one of the water molecules will be protonated, while the other one will lose a proton. The one that is protonated is the one that loses the proton, an acid, its protonated form will be its conjugate. The one that accepts, the one that loses its proton, the hydroxide would form will be its conjugate base, while the one that receives the proton is a base, while its protonated form will be the acid, and that protonated form we refer to it as the hydronium ion. Now, something here that water has a slight but important thing. It has been mathematically proven that the hydrogen ion concentration in water is about 10 raised to the power minus 3 molar. The hydroxide ion concentration is also about 10 raised to the power minus 7 molar. You also calculate the molar concentration of water itself, about 55.56 molar. Now, the dissociation constant for water, the dissociation constant, if you express it as mathematically, you express it as the product concentration over reactant concentration. What are the products? The products are the hydrogen ion and the hydroxide ion, while the reactant itself is the water that dissociates into the hydrogen and hydroxide ion. Now, if you do a rough calculation, one will find out that the dissociation constant for water, the dissociation constant for water is about 1.8 times 10 raised to the power minus 6 molar. That's 1.8 times 10 raised to the power minus 16 per liter, excuse me. Now, what that implies is that it tells you something about how much that reaction moves towards product generation. What it simply implies is that the equilibrium constant for the dissociation of water molecule is quite small, and it tells you a lot about how readily that reaction occurs. Like I said earlier, water molecules dissociate just, that means if you have about a billion water molecules, just one out of a billion dissociates. So the acid or the acidic behavior of water, hello? The acidic behavior of water here implies that your water molecule is what? Is a weak acid, because it doesn't dissociate readily now. And you can always differentiate a weak acid from a strong acid. In biological systems, weak acids are known to be very important. I will come to that shortly. Weak acids are known to serve important physiological roles. Now, I said something about water molecules the other time being very important in biological systems. We know very well that synthesis reactions involve generation of water molecule, while solvation reaction or hydrolysis reaction requires water molecules. When I say hydrolysis reaction requires water molecules to break down ester bonds, a donation of water to either of the two groups would cause what? Would cause a breakdown of ester bonds, like what you have in amides, in a peptide bond, the carbonyl NH group in the peptide bond that you find in peptides. So water molecules, they're generated during synthesis reaction, and they are also needed to break down products of those synthesis reactions. The presence of the hello, can you hear me, please? The presence of the two lone pairs of electron allows water molecule to carry out nucleophilic attack on groups. Now, if I would continue from there, I said something earlier that the water molecules can behave like acid and they can also behave as bases. So we all agree that water is amphoteric in nature. If it can behave like an acid, and it can also behave as a base. Now, I don't want to, I would want to go on to so moving forward, we've been, hello? Hello? Is there someone? Yes?
No, it's not a mistake, sir. Sorry, sir.
Okay. So you can mute yourself.
Sure.
Now, you can also define another constant, which is the ion product of water, as you can see on the screen. The dissociation constant for water is 1.8 times 10 raised to the power minus 16 mole per liter. If we cross multiply, you get another constant known as Kw, ion constant of water. Now, the ion constant of water is K multiplied by the water concentration, which is also equal to hydrogen ion concentration multiplied by hydroxide ion concentration. If you find the Kw using any of those two products, you would get a sum of 1.0 times 10 raised to the power minus 14. 1.0 times 10 raised to the power minus 14, if you extrapolate, you could always deduce that the hydrogen ion concentration multiplied by hydroxide ion concentration is 1.0 times 10 raised to the power minus 14. We can multiply both sides by the negative log of hydrogen ion concentration, by the negative log to base 10. If we do that, we could extrapolate terms of negative log of hydrogen ion concentration plus negative log of hydroxide ion concentration, which will be equal to minus 14. So if you do that, you get a term pH plus pOH will be equal to 14. Now the pH is just a measure of the hydrogen ion concentration in solutions. Now, why pH? You know very well that the hydrogen ion concentration can be expressed in molarity. If it is expressed in molarity, because water molecules dissociate quite slowly, you would probably be getting terms of hydrogen ion concentrations, which will be so minute to express in readily discernible terms. So Sorensen in 1909 introduced the term pH as the negative log of hydrogen ion concentration, so that one will be able to express the hydrogen ion concentrations in easily discernible form. And that form, from there, you observe that the hydrogen ion pH would range from between 1 to about 14. Now, the pH for pure water, the pH, there's always a neutral pH of 7 between 1 and 14, while pH values below 7 are known to tend towards acidic, while those greater than 7 tend towards what? Basic. Now, we find acids as proton donors earlier and the bases as proton acceptors. That is the definition stated by Bronsted. Others have defined acids and bases in terms of electron pair donor, electron pair donors, hydrogen ion, um, producer in aqueous solutions as defined by Arrhenius. Those that would produce hydroxide ions in solutions in aqueous solutions as defined by Arrhenius too. But the readily acceptable definition is that of acids as proton donors, while bases are regarded to as proton acceptors. Now, we already agree that water molecules behave like weak acids because they don't dissociate readily, while the stronger acids are those that would dissociate completely into their component ions in solutions. Now, the strong bases too are those that would readily give off hydroxide ion or take up hydrogen ion readily. Now, the strong bases too would ordinarily be completely dissociated in at high pH. Now, the pH scale, I mentioned earlier that the pH scale ranges from between 1 and 14. It's a logarithmic scale used to denote the relativity of hydrogen ion concentrations. Now, for hydrogen ion concentration of 10 raised to power minus 1 molar, the pH is the negative log of that 10 raised to power minus 1 molar, which will be equals to 1. For those with an hydrogen ion concentration of about 10 raised to power minus 14, the pH will therefore be what? 14. Now, for every 10 units difference. Okay, I'll come back to that. Now, the relationship between pH and pOH, I stated earlier from the ion product of water is pH plus pH equals 14. Now, what that implies is that if the pH or the hydrogen ion concentration is known, one would be able to calculate the pOH or pH as the case may be. There are several ways of calculating the pH if the hydrogen ion concentration is known or not known. The hydrogen ion concentration is known. A simple way of calculating pH, as we have in this example 1, is to calculate it as pH is the negative log of hydrogen ion concentration. Here, you have a pH of negative log of 3.2 times 10 raised to power minus 4. You get a pH value of about 3.5, which shows that that solution is acidic. Okay. So it shows that that solution is acidic. Now, okay, in example 2 here states that what is the pH of the solution whose hydroxide ion concentration is 4.0 times 10 raised to power minus 4 mole per liter. Now, you've been asked to calculate the pH where the hydroxide ion concentration is given. There are two. One should always calculate the pOH, which would be 3.4, and then find the pH using extrapolating from the term pH plus pH is equal to 14. So pH will therefore be 14 minus pH. That will be 14.4. That's 10.6. That's also a basic solution. Now, I said that functional groups that are weak acid have great stability. Now, the pH of the body left unchecked can result in severe metabolic abnormalities. Now, there are groups in our biomolecules. There are several groups in our biomolecules that assist with the resistance changes in pH. So we call such groups buffers. They behave like buffers. Now, there are physiological buffers that are found in the blood biological system. Now, physiological buffers majorly are component cell. An example of groups, functional groups that have capacity. An example of such group is the carboxylic group that you find in amino acids, as well as the amino group that you find attached to the alpha carbon of amino acids. Now, for the carboxylic groups are acidic in nature, and being acidic in nature, they would behave like acid, and when they behave like acid, they tend to ionize energy. The ability to ionize depends on them that's buffering capacity. The amino terminal too in amino acids, they also tend to take up protons and become ammonium ion. They could also donate. Now, the take home from here is that the carboxylic acid, when they donate their protons, they become basic. They become conjugate. Now, if a protonated ammonia group 2, if the protonated form of amine group, the protonated form of the amine group can donate. It behaves like an acid. By the time the proton, it starts you get the conjugate base of that acidic form of ammonia. So basically, the amine group can exist in the basic form or in the acidic form. The same thing too with the carboxylic group in amino acids. They could exist in the acidic form or in the basic form, as the case may be, or due to the point of ionization they have. If they have lost the hydrogen ion, they become basic. If they've taken up hydrogen ion, it could become basic or acidic, as the case may be. Now, these groups, the conjugate base conjugate acid pair, are central to the working of buffers. We know very well that buffers are solutions that resist changes in pH, and they are made up of two main components. The two main components of buffers are the acid, as well as conjugate, the salt of its conjugate base. I would find the term pH. the strength of an acid. The strength of an acid, or a weak acid as the case is here, can be described in terms of the Ka values. The Ka values are simply the acid dissociation constant. The Ka values, as the name implies, the acid dissociation constant is simply a measure of the product to reactant ratio. Simply a measure of the product to reactant ratio. So a product in a reaction could be the reactant in another reaction. The reactant in one reaction could be the product in another reaction. So one has to understand, is that reaction, are you having a donation of proton or an acceptance of proton? For instance, if a carboxylic group is serving as the reactant, if it is donating a proton, the carboxylate ion will be the base. The carboxylic group will be the acid. Now, the Ka for that reaction, where the acid is dissociating into its conjugate base, its conjugate base and the hydrogen ion. That's Ka. The Ka there will be a function, or it will simply be the concentration of the carboxylic group, or concentration of the carboxylate ion per the concentration of the carboxylic acid. So you have the base to acid ratio as your acid dissociation constant for such reactions. Now, the Ka, the larger the Ka, the larger the Ka for reaction, it shows that the reaction tends more towards the right, or more towards product formation. Now, if the Ka for a reaction is low, that means you have a low conversion of reactants to products. So the Ka for an acid can denote the strength of that acid, can tell us if that acid is a strong acid or a weak acid. A strong acid will readily dissociate to form its products. A weak acid will not dissociate readily from its product, hence having a low Ka value. Ka values for weak acid are majorly below 1. The Ka values for strong acids, such as hydrochloric acid, H2SO4, are mostly above 1. Now, for weak acid, the Ka values would be so small or minute that it would be better expressed in more appreciable forms, whereby the Ka values are converted into a logarithmic form. The logarithmic form will involve converting into pKa. pKa's, like the case of pH, will just be the negative log of Ka values. Now, it is expected that for a weak acid that has a low Ka value, for a weak acid that has a low Ka values, the pKa will be higher. For a strong acid which has a relatively higher Ka value, the pKa will be what? Will be low. So the lower the pKa, the stronger the acid is. The lower the pKa, the stronger acid is. Now the pKa, there is a term that describes the relationship between pH, pKa, and the concentration of base to acid. That term is referred to as the Henderson-Hasselbalch equation. The Henderson-Hasselbalch. Did I mute everybody? Hello. Now, the Henderson-Hasselbalch equation describes the behavior of weak acids and buffers. We know very well that the Henderson-Hasselbalch equation states that the pH is equals to pKa plus the log of conjugate base all over acid. Now, assuming that the concentration of acid and the concentration of the base and acid are equal at equimolar concentration of base and acid, the pH will be equals pKa plus log of 1, and that will be pH equals pKa plus 0. So pH will be equals pKa plus 0. At that point, it would be said that we can define the pKa as the pH when the base and the acid are present at equimolar concentration. At what point do you have the acid and base present at equimolar concentration? Take for instance, if you have an acid HA, you have 4 moles of an acid HA. If it dissociates midway, into hydrogen ion and a conjugate base A minus, you have, instead of 4 HA acid, you have 2 HA acid. How many moles of A minus do you have at that point? You also have 2 A minus. At that point, it is said that you have half neutralization has occurred. It's taken that the acid is undergoing a neutralization reaction with the base, so it has half dissociated. At that point of half neutralization, the pH is also equal to pKa because the ratio of base to acid are equal. They're just 2 out of the 4 acid that we started with. So the pKa can be defined as a pH when the acid and base are present at equimolar concentration. It could also be defined as the negative log of Ka. It could also be defined as the pH when the acid has undergone half neutralization. Okay, so I have been describing buffers. But before I describe buffers in mathematical terms further, I want to state that there are 2 main types of buffers. The first is the acidic buffers, buffers with a pH of below 7. acidic buffers, as the name implies, will be formed from two components, which are the weak acid and its conjugate base, or the salt of its conjugate base. While basic buffers could be formed from bases or weak bases and one of its salts too, one of the salt of the conjugate acid. So the two, we need to understand the fact that the resistance to pH change conferred on buffers by their two components. What it simply implies is that two components help to mop up either hydrogen ion or hydroxide ion, as the case may be. When you're having an increase in pH, that means the solution is tending towards being basic. The effect is that hydroxide ions are being the level of hydroxide ion is increasing. When the level of hydroxide ion is increasing, the buffers will resist changes in pH by ionizing to generate more hydrogen ion to mop up that hydroxide ion. On the other hand, too, where the hydrogen ion concentration is increasing and the pH is reducing, the components of the buffer, which is the basic component of the buffer, would also help mop up the hydrogen ion and keep the pH relatively constant. Now, for buffers can also be categorized into bicarbonate and non-bicarbonate buffer systems within the physiological systems. Talking about within the cell. There are also non-physiological buffers. Non-physiological buffers that are used in the laboratories to carry out experiments or to do in vitro, in test tube experiments. Now, these non-physiological buffers, a vivid example of a non-physiological buffer is the buffer obtained from acetic acid. That's the acetate buffer. Acetate buffer has acetic acid and the salt of acetate. An example of such salt is sodium acetate. Now, for an acetate buffer, the pH of an acetate buffer varies with the concentration of base to acid present in that buffer system. So if the concentration of base to acid is higher, the pH will be equals to pKa plus the value of log of base all over acid. Now, what will happen is that the pH will be greater than pKa for situations where the concentration of base is higher than that of the acid. Now, if the concentration of acid is higher compared to the concentration of base, what will happen is that the pH will be lower than the pKa. And what that also implies is that where you have according to the Henderson-Hasselbalch equation, where you have the pH is a variable, the pKa is a constant for different acids, then the ratio of base to acid is varies. Now, as you vary the ratio of base to acid, so does the pH varies. Now, where you have more base, it is expected that the pKa would rise. Or sorry, the pH would go higher than the pKa. Where you also have more acid in that buffer system, the pH will go lower than the pKa, going towards being acidic. Now, an instance where you have equimolar concentration of base to acid, at that point, for an acetic buffer, where you have the same amount of acetic acid and the same amount of acetate ion in that solution, the pH will be equal to pKa. Where the pH is equal to pKa, it is said that what? It is said that the pKa, you can use that to also define pKa of acetate buffer. Sorry, the pKa of acetic acid as the pH when the acetic acid and acetate ion are present at equimolar concentration. So varying the base to acid ratio would affect the pH. The bicarbonate and non-bicarbonate buffer system. The bicarbonate buffer system essentially is the major blood buffer system. Solutions of weak acid or bases and their conjugates exhibit buffering, as I've stated earlier. The ability to resist the change in pH following addition of strong acid or base. Since you have many metabolic reactions accompanied by release or uptake of protons, most intracellular reactions need to be buffered effectively so that metabolic conditions that would adversely affect the cell will not set in. Now, the mechanism of pH control. Buffer system consists of the weak acid and its ion for where you have an acidic buffer, but in cases of basic buffers, you would have a weak base and its cation, as the case may be. Now, the three major buffering systems that are found in physiological systems are the protein buffer, the hemoglobin buffer system, and then the minor buffering system consisting of phosphates, the phosphate that you find most readily in nucleic acids. Now, the carbonic acid bicarbonate buffering system. The main cause of the bicarbonate buffer system is that the carbon dioxide produced in cellular reactions can take up water in a reaction like bicarbonic anhydrase to form carbonic acid. The formation of this carbonic acid is also in equilibrium with the dissociation of carbonic acid into hydrogen ion and bicarbonate ion. That should be HCO3 minus. Now, it has its own limitations. It has its own limitations, amongst which are that it is limited by the availability of bicarbonate ions. So, though the body has some bicarbonate reserve that can mediate this. Now, it also only functions when respiratory system and control centers are working normally. Where there is a problem with the respiratory system, where carbon dioxide, oxygen ratios are malfunctioning, this bicarbonate buffer system may not function optimally. Where you have in the bicarbonate buffer system, there is an equilibrium established between the carbonic acid and bicarbonate ion based on the pH at that point. Now, the blood is known to have a pH of 7.4. Now, the pH of 7.4 for the blood, the pK of the carbonic acid, the dissociation of carbonic acid is about 6.1. If we do a rough mathematics using the Henderson-Hasselbalch equation, pH of 7.4 equals pK of 6.1 plus log of base over acid, would get the ratio of base to acid that is required to keep the blood pH at 7.4. That ratio of bicarbonate to acid would be a ratio of 20 to 1. So for every bicarbonate ion, there should always be 1 mole of carbonic acid to maintain the blood pH at 7.4. So there is always an interplay between where you have excess hydrogen ion. Where you have excess hydrogen ion, the bicarbonate ion will mop it up. Where you have excess hydroxide ion, the carbonic acid would also come to ionize and mop up the hydrogen ion into water. So that establishes a constancy in the level of hydrogen ion and hydroxide ion in the blood, and prevents a lot of metabolic abnormalities. So they would continue the class with a recap of the buffering systems. I would likely